Hello, 8th graders. Let's take a look at some systems of linear equations. Here we have two lines. They have different slopes, clearly, -3 for one of them and 2 for the other. So we know that they will intersect. A quick review of Chapter 4, we learned there that having the same slope is equivalent to the two lines being parallel. Of course, we have to make exception for the vertical line, which does not have a slope. We can say that all vertical lines are parallel. And then for any situation where we have two lines, neither of which is vertical, we can say that two lines are parallel if and only if they have the same slope. It works in both directions. So these two lines are not parallel. They will therefore intersect at a single point, and it is our task to find that point of intersection. We understand what we're doing geometrically as well as algebraically. We're looking for the point x comma y of the point of intersection. That's the geometry. Algebraically, that x and y of the point of intersection, when substituted into each equation, will make a true statement. That is the big picture of systems of linear equations. Now, one way to solve a system of linear equations is by graphing. We know how to graph lines. We only need 2 points to define a line. If you have 2 separate points, there is only one line that goes through those 2 points. And we often are interested, we sort of favor looking for where the lines cross the axes, the x and y intercepts, right? So for this first line, the most obvious point that's on this first line is 0, 1. That's the y-intercept, and it's staring us right in the face right there. As far as the x-intercept, where this line crosses the x-axis, well, that's where y is 0. So we need to do a little algebra, put a 0 in for y and solve for x. You should be able to do this mentally, subtract 1 from each side, and then divide each side by -3, right? Divide each side here by -3, you get x equals -1 over -3, which of course is positive. So you could eyeball the point 1/3, 0 with a sharp pencil on a piece of graph paper and plot the point 0, 1, connect them with a ruler, and you've got that line. Of course, you could use Desmos as well and get a very, very nice graph of the line. Down here, the second line, of course, goes through the y-axis at -9. We put a 0 in for x, y is -9. That's the y-intercept, and it's staring us right in the face. As far as the x-intercept, we put a 0 for y and solve for x, and it looks like we're going to get 9/2, right? X is 9/2 or 4.5. So again, you could graph those 2 points, connect them with a ruler, and you can then see where the 2 lines intersect, and that's your answer to that is your solution to the system of linear equations. So just a quick talking about the graphing method. Now we move on to algebraic ways of solving these systems of linear equations, which is the heart of Chapter 5. And traditionally, we talk about 2 different methods, the substitution method and the elimination method. And one message that I like to always give students at every level is be flexible. Be able to use any method that you think is the easiest, the one that you're most comfortable with in any situation. I try to display for you as many different approaches as possible. And sometimes I even take approaches that I wouldn't necessarily do myself just for instructional purposes. So let's now look at solving this system algebraically. One of the most fundamental concepts in mathematics is that when 2 quantities are equal, one can be substituted for the other. And so we look up here and we see that we have 2 things that are equal to y. This is -3x plus 1 is equal to y, and 2x minus 9 is equal to y. We can take this 3x plus 1 and substitute it for the y there, or the other way around, you'd get the same result with the things flip-flopped across the equal sign. So we now have this equation right here, which I began teaching to students in 7th grade. Strangely enough, the 7th grade textbook that we use does not have students solve equations like this, but knowing that they come up in the Algebra 1, I have students solve it, and it's not that difficult. This is something that most 7th graders mastered very quickly and know how to do for the rest of their lives. But we're now able to see something we did in 7th grade take on a new meaning. In 7th grade, when we're solving this equation, we're looking for the value of x that will make the left side equal to the right side. That's always what we're looking for in solving an algebra equation, what will make a true statement. And so we follow our general approach of doing the same thing to each side. And maybe we start out like this, subtracting 2x from each side. And I'm going to save a little time by combining a couple of steps. After subtracting 2x from each side, we want to subtract 1 from each side, of course. Over on the left side, we get negative 5x. And then on the right side, these add to 0 here on the left. These add to 0 on the right, so the right side is negative 10. And then we see now that x is 2, of course. We would divide each side by negative 5 and get x equals positive 2, negative 10 over negative 5. And when we solved equations like this in 7th grade, I urged you, go back and take this 2 and put it in for the x in the original equation here and here and see if you get a true statement. And negative 3x plus 1, if x is 2, it's negative 6 plus 1 or negative 5. And over here you have 2 times 2, x is 2, 4 minus 9, also negative 5. And therefore, you are 100% sure that 2 is the solution to that equation. But now there's a different take on it, a different interpretation. Remember the 2 t-tables we had up here before, right? I put t-tables up there before for the intercepts. Well, we now know that if x is 2, y will be negative 5. 2, comma, negative 5. That's the point of intersection of the 2 lines. And in terms of algebra, x equals 2, y equals negative 5, that's the only pair of x and y that will appear on both t-tables. Now, we might have stumbled upon that if we happen to choose 2 for x, put a 2 in here for x and you get y is negative 5. Put a 2 in here for x and you also get negative 5. You could have stumbled upon it, but we did it purposefully by solving the system of linear equations by the substitution method. Substituting negative 3x plus 1 here for the y there. We then had an equation in just the one letter x. We solve for x. Then we go back and substitute again. Substitute the x equals 2 in each equation and see that y is negative 5 both times, and that's the solution. Very nice. We'll move on to our second system now. Here's our second system of linear equations. And I talked earlier about flexibility. This time we have one equation in the slope-intercept form and another equation in the standard form. Well, the easiest way to solve this is again by substitution. Within this little universe we're operating in, within this system, y is equal to negative 2x minus 1. So we can take that quantity of negative 2x minus 1 and substitute it for y here. Now, a couple of things about this substitution. First, the entire y has to be multiplied by something. Both the negative 2x and the negative 1, both of those constitute y. So they both have to be multiplied by a number down here. The distributive property comes into play. We must employ the distributive property and insert parentheses. And notice I sort of coyly talked about the number down here. Well, that number is negative 2. I did that on purpose. If this had been a plus 2, the number that the y is being multiplied by would be 2, positive 2, but it's got a minus sign in front of it, so it's negative 2. This is trying to avoid common mistakes. So what you need to do is rewrite the second equation like this. And notice, right here, that is the second equation with negative 2x minus 1 substituted for the y. The parentheses are essential, and you have to realize that this number here is not 2, it's negative 2. So now we're going to get negative 3x plus 4x plus 2 equals 4, right? Negative 2 times negative 2x is positive plus 4x. Negative 2 times negative 1 is plus 2. Now we combine these two terms, which are both on the left side, so we simplify that left side. Ooh, this turns out to be a nice, easy one, because look at that. Negative 3x plus 4x is x, plus 2 equals 4. Subtracting 2 from each side, we get x equals 2 again. Isn't that interesting? Last time we got x equals 2 as well. Well, we're only half done. Remember, we're looking for the point of intersection of the two lines. And by the way, the two lines do have different slopes. This line here obviously has a slope of negative 2. For this one, we have to, we know how to convert this second equation into the slope-intercept form, isolate the y, and we would find that it does have a different slope than the first line. So there's a point of intersection. And let me set up a t-table now, two t-tables. Okay? We have, through our substitution method, determined that x is 2. So let's put 2 in for x in each t-table and see what we get for y. In the first equation, y is going to be equal to negative 2 times x minus 1, negative 2 times 2, x is 2, negative 4 minus 1, negative 5. Look at that. Wow, that looks familiar. And in the second equation, we'll do the same thing. Substitute 2 for x. This is a little harder. We get negative 6. Negative 3 times 2 is negative 6. Minus 2y equals 4. Add 6 to each side and get negative 2y equals 10. That was adding 6 to each side. Divide each side by negative 2 and y equals negative 5. Of course, we had to, once we got negative 5 here, we had to get negative 5 there as well. If we didn't, there would have been a problem. This is the whole point. There is a single combination of x and y that makes a true statement in both equations. And it happens to be 2 for x and negative 5 for y. That is the point of intersection. Were you to graph these two lines, and you certainly know how to do that, or you use Desmos, were you to graph these two lines, they would intersect at this point, known as the solution of the system. So that's system number 2. Let's move on to system number 3. Before we look at the so-called elimination method, I want to lay a little foundation for it and look at this, again, non-controversial equation statement that 2 plus 3 equals 5. What if we were to multiply each side by negative 2, or any number, right? Multiply each side by the same number, and of course, we would have to apply the distributive property. In order to multiply 2 plus 3 by something, you have to multiply each of the 2 and the 3 by that number. And of course, we see immediately what happens here. Negative 4 minus 6 equals negative 10. And there's still a true statement. This is the fundamental approach to solving algebra equations. Do the same thing to both sides and get an equivalent statement, an equivalent equation to the original. Now I have two non-controversial statements on the board, the same 2 plus 3 equals 5, and also negative 9 plus 1 equals negative 8. What would happen if we were to add the two left sides and add the two right sides? We'll do it term by term. 2 plus negative 9 is negative 7. 3 plus 1 is 4. And on the right side, 5 plus negative 8 is negative 3. Another true statement, right? And this is really the same concept of doing the same thing to each side. Because 2 plus 3 and 5 are equal to each other. So when we add 2 plus 3 to the left side and add 5 to the right side, we are adding the same thing to each side. So of course we get that true statement. These couple of concepts that I just looked at now, very non-controversial, are behind what is known as the elimination method. In this system of linear equations, both equations are in standard form, and that is when the elimination method is most useful. Now, I talked about flexibility earlier. Many times in math, in fact, the further you go, the more complex the math is that you're working on, the more ways there might be to solve the problem. And here, if you wanted to, you could solve each of these equations for y and then solve it like the first system, where they were both in slope-intercept form. Y equals mx plus b, and the other y equals mx plus b, and substitute like we did in the first. So you could do that here if you were willing to solve for y. You could solve one of them for y and substitute what y is equal to into the other equation and solve it like we did the second system. So please realize that there are always those possibilities. The elimination method is also known as the addition of equations method, for obvious reasons, as we'll see. And the idea is you want to add the two equations so that one of the variables goes away. You can eliminate the x to solve for y, or you can eliminate the y to solve for x. And one thing that's consistent about all the methods is you start out with two equations with an infinite number of solutions. You start out with two equations that both have x and y, and you somehow maneuver to a situation where you have just one letter, either the x or the y. You solve for it, and then you go back and get the other one. So there is that is the same about all the methods. Now, if we were to add these two equations as is, it wouldn't be helpful. Within our system, this is equal to negative 10. So if we were to add this to the left side and negative 10 to the right side, we'd get a true statement within the system, but it wouldn't help us because we'd have 3x plus 7y equals negative 29. What I just did there was add the two equations. But we still have an equation in both x and y, so it wasn't helpful. So what we need to do is strategically come up with equivalent equations so that when we add them, one of the variables will go away. So let's begin by eliminating x and solving for y. If we want to eliminate x, what we can do is multiply the first equation by 2 and the second equation by 5. Okay? Now, this is the one part, the one critical part of this method where you just have to think about it and figure out what works. I'm dealing with a non-cooperative marker here. I'm going to switch to a blue one from the red. I think I have to retire that red marker. Okay, so multiply the first equation, everything on both sides, by 2, and the second equation, everything on both sides, by 5. Why did I do that? Because when I get those two equivalent equations and add them, the x terms will add to 0 and be eliminated. Here's the new first equation, okay? 10x plus 8y equals negative 20. Notice, it's the distributive property on the left, right? You have to multiply each of these terms by 2, but you also have to multiply the right side by 2, of course. Down here, the new look to the second equation is going to be negative 10x plus 15y equals, negative 45? 5 times, oh no, negative 95. That was bad. 5 times 19 is 95, right? 50, yeah. So negative 95. Sometimes the numbers get a little big or small. The absolute values get big in some of the numbers, even when you start out with relatively small ones. But look, you know, you now add these two equations, and the x terms add to 0 and get eliminated. These two add to 0. That's why we multiplied the first equation by 2 and the second equation by 5. You have to strategically figure that out. And then the rest of it just falls into place. 8y plus 15y is 23y. And negative 20 plus negative 95 is negative 115. Now that looks kind of, might look, ooh, that doesn't look very promising, right, to come out to a nice solution, but it will. Look what happens. Divide each side by 23, and you get y equals, guess what? Y is negative 5. Ooh, what a surprise. Not really. Y is negative 5. If you haven't figured it out by this point, ladies and gentlemen, here are my notes for this video. The very first thing I did was right at the top, 2 comma negative 5. I chose that as the solution for each of the systems. And then when I created the equations in each system, I had to make sure that 2 comma negative 5, x equals 2, y equals negative 5, will make a true statement in all of these equations. If you can sometimes get inside the head of your teacher, I know that's a scary thought sometimes, but if you can start to think like the teacher, sort of figure out how's the teacher doing what he or she is doing, you'll go a long way towards success in school, believe me. Try to anticipate what the teacher will do next. Try to think what you would do in the teacher's position, because there's a very common saying in education that you really don't know a subject until you have to teach it. And I can attest to that. I could do all of this math 21 plus years ago when I started teaching Algebra 1. I could do it successfully, but I know that 21 years ago or even 10 years ago I wasn't explaining it the way I am now, because when you have to teach something, you learn it on a very deep level, and that should be your goal, to learn everything you learn in every subject on a deep level that makes it meaningful to you, not just to get the right answer. Now, we could at this point take that y equals negative 5 and substitute it for the y here and solve for x. Substitute it for the y here and solve for x. And I think you know what that's going to turn out to be. I just showed you. The x is going to turn out to be 2. But just to get the practice of the elimination method, let's now do the elimination method again. The first time we eliminated the x's to solve for y. This time we're going to eliminate the y's to solve for x. Here's the same system again. Looking at the y terms, we see a 4y and a 3y. Now, the elimination method is sometimes called the addition of equations method. You can also subtract the two equations in this elimination method. Subtraction is generally a little bit harder than addition, so you might want to stay away from subtraction, although for flexibility, there are times when I look at a system and I'll say, hey, if I just subtract them, I'm going to be good. So you should be able to do it, but in this case, I'm going to work it out so that we add rather than subtract. So I notice that there are two plus signs. The coefficient on the y coefficient, the number that the y is being multiplied by, in each case is positive. So what I'm going to do is I'm going to choose one of my numbers that I multiply each equation by. I'm going to make one of them be negative. How about negative 3 there, and then 4 there? Now, it could have been the other way around. This could have been negative 4, and that could have been 3. Or they could have both been positive. If they were both positive, you'd have to subtract. But this is a good way to solve this system. So let's come down here now and write the new first equation, right? Multiplying everything in the first equation by negative 3, we get negative 15x minus 12y equals negative 3 times negative 10 equals positive 30. Remember to multiply everything on both sides by that same number, negative 3. And the new second equation is going to be 4 times negative 2x, negative 8x, 4 times 3y plus 12y, and 4 times negative 19, negative 76, I think, negative 76, right? Okay, now you look down here and you see, well, if we add these two equations, the y terms will go away. Why is that? Because we made it happen. See, some of this is strategic in the elimination method. You do something because you know it will work, and the rest of it is just straightforward, solving algebra equations. Adding the two left sides, these y terms get eliminated, they add to 0, and we get negative 23x equals, and then over here, negative 46, right? Dividing each side by negative 23, canceling, look at that, x equals 2. And so, remembering from previously when we solved for y, we got y was negative 5. So, there's the solution, x equals 2 and y equals negative 5. When you graph these two lines, they will intersect at the point 2 comma negative 5, and x equals 2 and y equals negative 5 is the only combination of x and y that will make a true statement in both equations. And by the way, one last quick word about equivalent equations, right? What I call down here the new version or the new look to equation number 1, if you go to Desmos and you type in 5x plus 4y equals negative 10, and then you type in down here this negative 15x minus 12y equals 30 on a second line in Desmos. Of course, the two lines that get graphed are going to be right on top of each other. They are identical lines, they just look different. We call that equivalent equations. When the two equations are equivalent, their graphs are the same line right on top of each other. And why is this equation here equivalent to the one up here? Because we multiplied through by negative 3. And then this equation, the new look of the second equation, is the same line as what you got from the original second equation. So we'll call it quits for now. There are other things to think about, other situations. In your textbook, in the Algebra 1 textbook, there's a lesson in Chapter 5 called Special Systems. Now those special systems are where the two lines have the same slope. I say the two lines have the same slope because there are actually two possibilities. If you have two separate distinct lines with the same slope, you can model it like this. They're parallel. We talked about that earlier. Therefore, there's no solution. There's no point of intersection. Two parallel lines do not intersect. And there's no value of x and y that will make a true statement in both equations. No solution to the system. But the other thing that can happen when you have, again, two lines with the same slope is they could potentially be really the same line in disguise. So that in that situation, what we say is not that there's no solution, but we say that there are an infinite number of solutions because every point on this line is also on this line because they are in fact the same line. That in a nutshell is Chapter 5, the kinds of systems that we just solved where there's a single solution, a single point of intersection, and then the two other special situations where the two lines have the same slope, which we'll deal with. It's not difficult. It's a really fun chapter, Chapter 5. And one last thing I'd like to say before closing off is that in Chapter 5, when we solve systems of linear equations, there are, I'll say, an infinite number of word problems that can be devised that are solved by solving these system of linear equations. They can be word problems involving the prices of tickets to a show, coins, having a certain number of quarters, a certain number of nickels, and adding up to a certain total. You'll see when we get to it, there are word problems that we're going to have to negotiate our way through by solving systems of linear equations. So long for now, 8th graders. Systems of linear equations. It's one of the big topics